Thank you very much. Those two, expecting to see Lawrence, one of our PhD students, I apologize. I will do my best to fill in for him, but he was very much under the weather and sent his apologies, but I would encourage you to try and get him back, as he's a wonderful, wonderful speaker. So I shall share my screen now. Probably start with this one. I wasn't planning to show this one, but just, you know, as Paul's introduction started, just, you know, one of those reminders. But my own vice chancellor and dean get this one wrong all the time.
Oh, fair enough. I'm in good company then.
Some sort of Freudian slip, very disappointed that somehow it's not AA Mill, but there you go. Okay, so filling in for, I apologize for the backlighting, but the kids are in bed and I'm sort of limited to where I can actually sit right now. So not much I can do about that. I just realized I look like a dark silhouette. This is a talk that it sort of sprung up about a year ago. I'd given a few other public talks, some of which I'd given with you folks a couple of years ago. But one of the questions that always comes up when I'm in schools and colleges and public talks as a whole are, you know, what are my favorite things in the universe? What are my favorite objects? And so I went away and I thought about it a little bit and started to make my own list of my favorite objects, whether they were near, whether they were far. And as I compiled them, I realized the things that were starting to fall onto my list kind of fell into the extreme, sort of a Guinness Book of Records sort of list. You know, the things that I remembered off the top of my head were things like, you know, the hottest place in the universe, the coldest place in the universe, you know, the biggest, the smallest, that sort of thing. And so I sort of rearranged it a little bit and built it around a bit of a TripAdvisor top 10, but also a little bit of sort of Guinness Book of Records sort of things. And so let's see if I can get this to work. Okay. So the way I've sort of broken it down is along these lines. So I won't read them all right now. They sort of speak for themselves. I have different versions of this talk. I've got talks of, you know, like when I go into primary schools, it could be, you know, even foundation year, early years, so 5, 6, 7-year-olds. And, you know, there's slight variance on what I actually present. The things that are always the most popular with the kids, without a doubt, are the things like the smelliest place in space. And I'll tell you what that really means in a few minutes. And things like the loudest thing in space. That's a bit more of an interactive thing, which I'm not going to attempt via Zoom, but I'll give you an idea of the sort of thing I might do if I was doing this in a school, for example. So those are the sorts of things that I'm going to walk through. Time-wise, probably the first few I spend a little bit more time on because it sets the stage for some of the things later on. So if you feel halfway through that we've not made progress on going through the top 10, I promise it does pick up towards the latter half as I whip through the remaining sort of 6 or so in a fairly rapid fashion. Some of these you will have seen before. Some of them you won't have seen before. Many of them you won't agree with. They won't mesh with your own favorite things, your top 10 list. I'm more than happy to take on board any suggestions afterward. If I've missed something really obvious, you know, maybe I should have put something in there to reflect the discovery of phosphine in the atmosphere of Venus, maybe. I'm not quite sure what I would have labeled it. If I was a cynic, I might say the most overblown thing in space, but I won't say that right now. We can discuss that later if we like. But this is a sort of the tack that I'm going to take as I go through right now. So, you know, start right off with the wettest place in space. Now, when I talk about wetness here, I'm really just talking about water and liquid water. And the only place that we know right now in the universe, and almost certainly won't be the only place in the universe, but the only place that we know right now with liquid water on its surface today is, not surprisingly, where we're sitting right now on planet Earth. Now, it's almost certainly the case that Mars had liquid water on its surface, you know, 3.5–4 billion years ago during its earliest phases. But thus far, we haven't found any liquid water on the surface of anything else. But that's not even in our own solar system, if you like, the wettest place, if we are talking about liquid water. We only have to look at the moons of Jupiter and Saturn. In particular, we've got Europa here on the left and Enceladus here on the right. Those are gigantic balls of briny salt water with a thick, couple 100-mile thick layer of ice on top. And the reason we know about that liquid water is, you can see it in pictures here, particularly with Enceladus, which was really studied by the Cassini mission, which basically flew through these plumes right here. And those plumes, that's water. And they're just geysers of briny salt water that has been released from beneath that icy surface. Because as Enceladus, as the moons are going around their host planets, they feel tides. Now, in this case, these moons are so tiny compared to Jupiter and Saturn, they don't really inflict much in the way of tidal effects on Jupiter or Saturn in the way that, say, the moon's tides affects, the water here on Earth. But what does happen is the tidal influence of the big planet on the little moon is quite strong. And so those moons get squished and tugged and pulled as they move around due to tidal forces. And those tidal forces, every once in a while, through this stretching compression related to tidal forces, cracks the ice. And when that happens, you get a geyser that shoots up water. And we see it this is a Hubble Space Telescope image of Europa, and it's not maybe quite so spectacular, but these little white bits that you see above the surface, again, that is subsurface liquid water that's been released by the cracking in the surface ice, much like we see with Enceladus. There are planned missions in the coming decades. NASA, you can look up the Europa Clipper mission. One of the jobs of those missions is to fly right through those plumes of water, scoop up as much as it can, and analyze it. The reason being, if you're looking for life outside of planet Earth, this might be a reasonable place to look for it. You're not going to be finding, Aquaman or piranhas or things like that beneath the surface. But in terms of the temperature, the acidity, the salinity, the salt content, it's sort of the right conditions for that first, nascent microbial life to appear. It's no guarantee it will be there, but the basic building blocks and conditions are really conducive or not wildly different than what you might have found very early on Earth. So there is some hope that maybe there'll be something there, and that's one of the goals of those missions, like the Europa Clipper mission, is to search for those first signs of life. There is liquid water elsewhere, or there's water elsewhere. There's icy water on the surface. On the surface of the moon, there's ice. Probably in the poles at Mercury, deep in the craters, there's probably water ice. Looks like beneath the south pole of Mars, it looks through radar imaging, it looks like there's probably possibly some liquid water beneath the surface. It's not like a beautiful crystal clear lake. It's probably very sludgy, muddy sort of stuff, but there's the potential for some liquid water beneath the surface. So again, if you are thinking about potentially finding sort of that microbial early life, that might not be the worst place to look. Not on the surface. There's going to be absolutely no life that's going to survive on the surface of Mars due to lack of a magnetic field, blasting apart anything that actually did try to form on the surface. But subsurface, there's the potential for that, again, that those first building blocks of microbial life might exist actually there. And there's twice as much water, just for example, twice as much water under the surface of Europa than there is in all the oceans here on Earth. So there is an enormous amount of water out there, significantly, if you like, wetter than it is planet Earth, just not on the surface. But that is just scraping the bottom of the barrel. That is just scraping the surface. There is stuff that is way wetter out there. And this is the current record holder. It has a very unromantic name. You can read the name across the top. It is a supermassive black hole. very, very far away. It's got a redshift of 4. If you're thinking about looking back in time, it's about 12 billion years look back time. So it's way on the other side of the universe. And lurking in the middle of this cloud, for scale, this is about 1,000 times the size of the solar system across. This is an artist representation. The images don't look quite so spectacular. Down in the center is a supermassive black hole. It weighs about 20 billion times the mass of the sun. So it's very, very, very heavy relative to other black holes. I'll come back to in just a second. But the interesting thing from the perspective of the search for life, in the sense of looking for water, is that this cloud of dust and gas that surrounds the supermassive black hole, it's got an enormous amount of water vapor. It's not liquid water, it's in a gas form, and it's very hot, probably about 300 degrees Celsius. So it's, superheated steam, if you like. But if you point a telescope, sort of the telescope you might have at Jodrell Bank, something that's sensitive to the radio waves and the millimeter waves rather than a traditional optical light that we look at with our telescopes, you can pick out various signatures that are that tell you something about the water content, and not just water, but any other molecule that might be present. We've discovered about 200 molecules in space. It's still a drop in the bucket of all the molecules that are out there, but as telescopes get stronger and more powerful, we've discovered more and more and more molecules. And in this particular cloud around this supermassive black hole, when you take a telescope that's sensitive to the millimeter waves, we can see this spectral line, and it doesn't look particularly spectacular, and by itself doesn't tell you a whole lot, but by doing modeling of the temperature, the content, the magnetic field around the region, we can figure out that this particular line, just looks like more or less any other line, is due to water. And it's a complicated way of writing it, but what it is if you take a water molecule, which you probably realize is H2O, 2 hydrogen atoms bonded with an oxygen atom, and that water molecule can spin in different directions, it can vibrate in different directions. Every time it vibrates and spins, it gives off radiation, and that radiation comes out with sort of a very specific fingerprint in frequency or wavelength. And so this is one particular way of spinning a water molecule, and you get this emission line, which is due to water. And so you can map across the cloud and add up how strong that line is at different places, and therefore add up how much water vapor is sitting inside this cloud. And you sort of can see the punchline there at the top. When you add up across this enormous cloud, it's 140 trillion times the amount of water that exists on Earth. And there may be some other system out there that has even more water, but again, this is just one random system out of billions, hundreds of billions, possibly even more systems. So, if this is representative of all of those systems out there, there is an enormous, enormous amount of water. Now, it doesn't necessarily mean that you're going to find life. The conditions inside of this cloud are not right for the development of life, but that fundamental building block that we think is important for, at least for complex biological life, which is water, there is an enormous amount of it out there around the universe. This is the current record holder. So in that sense, this is the wettest place in the universe that we know about. And just to stay on the topic, just for a couple more minutes on black holes, because it touches on something maybe that if Lawrence had been here, he may have talked about. And I think Mikkel Christensen was either here or coming up soon to give you guys a talk on active galactic nuclei. So this is a plot showing maybe 50 or so supermassive black holes. And what I'm plotting along here, along the horizontal direction, as I move to the right, galaxies get bigger and bigger. And vertically, as I go up, black holes get bigger and bigger. So every galaxy, effectively, that we know about has got something like I just showed you previously, a supermassive black hole sitting at the center of the galaxy. Our Milky Way is exactly the same. Here's our Milky Way down here. We have a supermassive black hole in the center. It's not a particularly, we're not a particularly gigantic galaxy with a particularly gigantic black hole, but there we are. The system I just showed you would be sitting up at the top end over here. Now, the main thing I want to show you here is that when I take big galaxies, which over here, they always have big black holes. If I take small galaxies, they've got small black holes. If I just throw down 50 points, it's not random. So what you can look at that and say there's something here which drives this. These points are not random. Why is it that big black holes know they're supposed to live inside of a big galaxy? Or conversely, why is it that big galaxies know they're supposed to, house a big black hole? So it's not random. And so you might think, okay, well, there's nothing particularly crazy about that. Big galaxies have big black holes. Okay, that's fine. But it's important when we talk about, we use terms like supermassive black holes, but the scale is something we kind of forget about. We think of these things as gigantic, all-encompassing, absorbing all kinds of stuff around them, gigantic, terrifying things, the stuff of science fiction films. But even these gigantic supermassive black holes, compared to the size of the galaxy, and are tiny, tiny, tiny little things, just tiny little drop in the bucket. And I guess the analogy that I like to use here is if you thought of the UK and you covered the UK in sand, just gray sand, each grain of sand, a millimeter in size, let's say, just covered the entire country. And then you walked right to the geographical center of the UK, and you went there and you looked down, and what did you see? You saw instead of all of the other gray grains of sand, you saw one red grain of sand was also, say, a millimeter in size. Okay, you might think that's an incredible coincidence that there's only one red grain of sand and it just happens to sit right in the middle, but maybe you'll accept that coincidence for the time being. And then let's say you cross the channel, you go into, say, Bulgaria. Bulgaria is exactly half the size of the UK. Now, if Bulgaria was covered in exactly the same gray sand, all of it's 1 millimeter in size. You wander to the geographical center of Bulgaria, and then lo and behold, what do you find? You find one red grain of sand, but it's exactly half the size of all the other ones. That it seems to know that Bulgaria is half the size, so that grain of sand right there in the center should be half the size. And you could go to Spain, do exactly the same thing. Spain is 5 times the size of the UK. You walk to the center of Spain. The rest of the country is covered in exactly the same gray sand, but then there's a 5 millimeter grain red sand sitting there in the center. And you go to Australia, which is 30 times larger, and you find a grain of sand which is 30 times larger. And so you might start to question, how is it possible? Why does this, in this case, in the center of Australia, why is there a 30 millimeter red grain in this sea of gray grains that are all 1 millimeter in size, sitting right at exactly the center? Why is it when I go to Russia, there's a 100 millimeter size red grain sitting right there at the center? Well, all the other grains of sand are exactly the same as everywhere else. And so it opens up this question about nature versus nurture. Is it the black hole itself that somehow sets the characteristics of the galaxy, even though it's on a scale which is billions and billions of times smaller than the size of the galaxy? Or does somehow the size of the galaxy know when it's supposed to stop growing a black hole in its center? And this is one of the sort of mysteries that we still have active in astronomy. It's something that we're involved with, and something that Mikkel Christensen, who, like I said, will be speaking or has spoken there, part of his PhD research, is trying to understand why it is there is this correlation. Why do galaxies know exactly how big the black hole is supposed to be in the center, even though the scales are, just orders and orders and orders of magnitude away from each other? So a fantastic mystery. It may not be a Nobel Prize winning mystery, but this is a very high profile problem that exists in astronomy today. So let's move on to the next part. I guess maybe one more thing related to black holes, and I think this probably touches on the talk I gave there with you folks a couple of years ago. We often think of black holes, the way I've described them, it sounds exciting, and it is from a scientific perspective and a mathematical perspective, trying to understand the physics of these black holes. But we don't necessarily think of them as having a practical application in the real world in our day-to-day lives. So this is one of the things that we do have to remind funding agencies, governments, when we're talking about the research we do. Okay, this is not why we do the research, but trying to understand the sorts of relationships that I've talked about there and the physics associated with black holes and supermassive black holes. It requires you and demands you to develop new technologies to try to answer those questions. And so some technologies that impact on us today, for most of us, we're connected to Wi-Fi, where we're sitting right now, just like I am. That invention of Wi-Fi, Spinoff technology in the search for primordial black holes that Stephen Hawking had postulated existed. They were never discovered, but it led to some wonderful technology that the Australian government now has the worldwide patent for Wi-Fi, and based on a technique called Fourier transform, sifting through noise, trying to search for these evaporating primordial black holes. Like I said, never were found, but Wi-Fi was a spin-off in trying to search for these sorts of black holes. And things like the sat-nav, GPS, Google Maps, they all hinge on the anchoring of the 30 to 40 global positioning satellites that we have orbiting around us to a background reference frame, if you like, latitude and longitude, if you like, on the sky. But the stars are they move around too much. As you know, you different epochs, 1950, 2000, et cetera, they provide too much motion for the simplest way of linking GPS and sat-nav, Google Maps, et cetera, to figure out where you are standing at any given time. And so those satellites get linked, get anchored, if you like, to what's called the International Celestial Reference Frame, which is a set of 200 supermassive black holes along the lines of what I started with, that are, again, so far away that you don't have to worry about things like B1950, J2000, the actual epochs. These things move, nano arc seconds on the sky every decade or so. And so, yes, they do get updated with the celestial reference frame gets updated every decade or so. But we're talking about updating the 9th and 10th decimal place in the RA and DEC, if you like, on those supermassive black holes. Those are the things that provide the anchor that allow you to do Google Maps and sat-nav and GPS, etc. And even spin-off technologies like X-ray scanning devices came about. Spin-off companies like this one, American Science and Engineering, who developed the X-ray technology for the very first generation of X-ray missions. Okay, so that's enough about black hole. Well, not quite enough about black holes. One more little thing, and this is one of my favorite ones, and certainly when I'm in schools, one of the most favorite ones with kids, and that is the smelliest place in space. Now, again, we don't normally associate smell with space, largely because normally, you zeroth order, you think of space as being a vacuum. There's nothing there, so there's nothing to smell. If you open up the mask on your spacesuit, you're not going to be a whole lot to breathe in, so you're not going to last very long. But as empty and as near perfect a vacuum as space is, it's not a perfect vacuum. And obviously, as you move through space, you run into things like gas clouds, which are far away from a vacuum. And one particular cloud that we've studied in incredible detail is a big one around the supermassive black hole in the center of the Milky Way. It's called Sagittarius B2. It's a cloud that's much, much smaller than the one I just talked about on the other side of the universe. And this one weighs about 1,000 times the mass of the sun. So it's fairly large in that sense, but completely different scales from the one I just talked about before. But because it's so close, it does mean that you can use these radio and millimeter wave telescopes and then map out the molecules in exquisite detail as you move across the cloud. And you can get, because it's so nearby, it's just much easier to observe. It's much brighter, if you like, but brighter in the radio and brighter in the millimeter waves. And it means that you can study more and more molecules. And we've been able to measure dozens and dozens of molecules to very high precision mapped across this entire cloud. And you might ask the question then, okay, It's a cloud filled with molecules. If I open my mask, my helmet, what does it actually smell like? Well, it's no longer a perfect vacuum, you would still die. But that aside, if you could breathe in and sort of get what is the overarching aroma, if you'd like, if you could suck all of that into your nose and smell it, what you would find is that first, one of the overall smell, I'll skip to the very bottom one, it smells mostly like raspberries and rum, and that's due to something called ethyl formate. Basically, if you mix an acid with ethanol or ethyl alcohol, you get this thing called ethyl formate, and it smells like raspberries and rum. So the overarching smell of this cloud is raspberry and rum. Very nice. But we can also measure with exquisite detail exactly how much ethanol or ethyl alcohol is in this thing. And there are billions of liters of alcohol spread throughout this cloud. And the way I tried to bring it into terms that we would understand, there's enough ethyl alcohol to fill 400 trillion pints of beer. And so to give it a bit more context, you can sort of read it there. Every single person on Earth would need to drink 300,000 pints a day for 1 billion years to empty this single cloud of the amount of alcohol that sits there. So it's a challenge some of you might be willing to give a go. And I think I saw at least 1 pint in there before we started sharing screens. So it's a challenge, let's say, that we'll set. But that right now, in terms of what we've been able to determine, is overall the smelliest place in space. And overall, it smells actually pretty nice, raspberries and rum. But what you can do is you can move into certain parts of the cloud and you can measure what does it smell in this part of the cloud versus, say, this part of the cloud. And what we've been able to determine is that there's an enormous amount of hydrogen sulfide in this one cloud. Hydrogen sulfide, for those who don't know, if you just replace the oxygen in H2O with sulfur and make it H2S, this is what you get, hydrogen sulfide. It is the thing that gives you the, if you like, the rotten egg smell when you pass gas. And if you add up how much hydrogen sulfide is in this cloud, it adds up to a big number. It would require every single person on Earth would have to pass gas every second for the next 100 million years to create the same amount of hydrogen sulfide that sits in this one cloud. So when I talk about the smelliest place in space, right now, I think you could probably say that that would be the winner. And I can go back to a school a year later and they will still remember that point. Now, okay, from the wettest, the smelliest, let's move on to the most expensive or like the most valuable. This is a random, what appears to be just a random star in the sky. It's about maybe half the mass of the sun. It's a K-dwarf. And it's called 55 Cancri. It's if you're in a dark site, it's a naked eye star. It's about 6 magnitude, just a tiny bit brighter than 6 magnitude. If you are up now at early hours, 3 a.m., 3 a.m. in the morning, it's well accessible. So it's better to observe sort of in the new year, but you could see it now if you're up at the crack of dawn. It's what's unique or special about it is that it's in a tiny little postage stamp size of the sky where the NASA Kepler mission surveyed over and over and over and took gazillions and gazillions of photos. And what the Kepler mission was trying to do was search for extrasolar planets. And the way that it worked was they take snapshot after snapshot after snapshot, and then for every star in the field, they measure the brightness in that snapshot, and then the next one, and the next one, and the next one. And if you're lucky, you'll have a planet pass in front of the star and block that tiny bit of the light. And so the light curve of the star will show a little dip. If it took the planet a year to go around, every year you get this little dip in the light curve as the planet went by. And this is how we've discovered thousands and thousands of extrasolar planetary systems now via this transiting property. And 55 Cancri has something like at least 5, maybe 6 planets around it. And one of those planets, 55 Cancri E, is a really special one. Now, this, not only do we know about the existence of the planet, because we've measured the shadow cast, if you like, by the planet as it passes in front of the star. And by looking at the light curve, we can actually tell how big the planet is. So we know the knowledge of the size of the planet. Now these stars are so bright, you can actually point a telescope at them and spread the light out into a spectrum and get really high signal to noise. And we look at all of the sort of absorption lines. And because it's so nearby and so bright, really high signal to noise, what that means is if you take spectrum after spectrum after spectrum, you can see the tidal effect of the planets going around the star. It causes the star to move a little bit, it wobbles a little bit. So as you take a spectrum, you will see the spectral lines wobble a little bit. So that also tells you there's a planet there, but more importantly, it tells you how heavy the planet is. So with the knowledge of how heavy the planet is, plus how big it is, it tells you something about the density. And if you know how dense the planet is, you can make some inferences as to what that planet is actually made of, given its density. And this one, 55 Cancri E, best guess is that it's about the size of Earth, maybe twice the size of planet Earth, but given its density and likely composition, the vast majority of it is going to be diamond. And if you take the current value of diamond today, the value of that planet is about 1 billion trillion pounds. Or if you think of it in terms of the Earth's gross domestic product, you can buy the planet Earth 1 billion times over. If Elon Musk flies out there and grabs a hold of it and drags it back, well, of course, you saturate the diamond market and then the value plummets and it's not worth anything. So you'd have to drip feed us diamonds. But there's in terms of just sheer value, and there probably are other ones out there that are more valuable in that sense. But in terms of things that we could measure, quantify in terms of pounds, if you like, this is the current record holder as the most expensive thing in outer space. They don't have to go quite as far as that planet, which is, I want to say it's between 40 and 60 light years away. You can just stick within our solar system. And well, of course, you can find diamonds here on Earth, but if you leave Earth, if you pop over to Uranus and Neptune and start working your way down through the atmosphere, the pressure grows and the pressure grows and the pressure grows. And as you know, hopefully, diamonds come about from basically taking carbon and crushing it under extreme pressure, deep within the planet Earth. You take, if you like, carbon, charcoal, coal, you can crush it into diamonds given the intense pressures that exist deeper in the Earth. Same thing happens in the atmospheres of Uranus and Neptune. You go deeper and deeper and deeper, pressure increases, and we know the atmospheres of Uranus and Neptune are filled with carbon-rich molecules, hydrocarbons. So as you go to deeper and deeper into the atmosphere, the pressure eventually gets to the point where you can take those hydrocarbons and crush them into micro diamonds. So they're not the sort of the cartoon style of diamonds that you see here in the accompanying diagram, but these would be microscopic scale ones. But if you take your best guess as to what we think the hydrocarbon content is in the atmospheres of Uranus and Neptune, you can make a best guess estimate as to how much diamond is actually in there. And it works out to, it's a nice number. It's not a crazy big number. It's about 10 billion pounds worth of diamonds, several millions of carats tied up in there. That would probably be more or less pay for the cost of the mission to actually get out there, if you like. So it sounds like a big number, but it costs a lot of money to go and get it. On the other hand, once you've scooped, if you could develop something that could go in and scoop out all these micro diamonds and turn them into something like that sort of pound value that you see there, they will reform. The atmosphere is very rich in hydrocarbon and it's circulating around. And so the rich reservoir of hydrocarbons in the outer part of the atmosphere will eventually fall down to the inner part and create more micro diamonds. Probably not worth the effort of doing so. Maybe if you're out there, you might send a probe deep down as far as you can and test this theory that the atmosphere is filled with micro diamonds. But this is something that until maybe a year or two ago, I had no idea about this. Something I've only learned very, very recently. Kind of interesting. I'm going to spend just a few minutes on some nuclear physics, if you like, and then I'll wrap up in rapid style the last few things. And this is broadly the source of everything now, and that's stars. And then I think we all know this as you look around the room where you're sitting right now. Basically, everything that you can see around you, started its life off in a star. Just as Carl Sagan said back in the day, we are star stuff, and that's the case. Outside of hydrogen and helium, tiny bit of lithium, that which came about in the Big Bang nucleosynthesis. More or less everything else in the universe, in the periodic table, came about through some sort of nuclear physics process inside of stars. So I'm just going to break it down into two types: big stars and sort of stars like ours, smallish stars. So I take stars that are maybe 10 to 100 times heavier than the sun. One of them explodes every decade or so in the Milky Way. An enormous amount of energy, billion times the most powerful weapon on Earth, the SAR bomb. So there's an incredible amount of energy, which can be scary if one goes off next to you and evaporates your biosphere, which can happen. But more importantly, the good thing about them is that everything that you see around us, again, came from one of these exploding stars, or a large fraction of them came from these sorts of exploding stars. And these sort of supernova remnants, which are spectacular to observe. The different colors that you were seeing there are different chemical elements that were synthesized inside of the star. Now, as the star is blown apart, the outer atmosphere of the star is blown apart, you're seeing those chemical elements getting spread out into the interstellar medium, which eventually get reincorporated into the next generation of stars and planetary systems, et cetera, et cetera. So if I look at a periodic table, it's a different way of looking at a periodic table, and you may have seen variants of one like this, where the color coding now is by what sort of, if you like, star is responsible for the chemical element. And so for the things that are all here in green, those are the exploding stars that I've just talked about. Big, heavy stars, massive stars when they explode. And things like oxygen and fluorine and neon and sodium and magnesium, and silicon, potassium, calcium, most of the things up to iron. So that first third of the periodic table, and some parts afterwards, come about from exactly what I just told you right there. At the end of the lifetime of a massive star, it's used up all of its hydrogen in nuclear fusion, and eventually the core can't support itself, it collapses, there's a big explosion, and that's where all these chemical elements come from. The way that those chemical elements, just very quickly, nuclear physics in sort of 30 seconds, most of those elements up to iron are built through, the fundamental building block is this one up here, helium. Helium is 2 protons and 2 neutrons. If you take, say, for example, 3 helium, so each one with 2 protons, and you squish them together, fuse them together, you can form carbon. So the 2 means protons. If I squish 3 of them together, I can form carbon. If I fuse another helium onto carbon, then I can create oxygen. If I fuse another one onto oxygen, I can create neon. And so I keep adding these building blocks of helium, or what we call alpha particles, on top of each other. And it allows me to work my way up to about a third of the periodic table. That is what nuclear fusion is. You are fusing these particles, these elements together, these nuclei of helium. Now, part of the problem is, think back, if you can remember, protons have a positive charge, and neutrons, which are the other component of helium, for example, 2 protons, 2 neutrons. Protons are positive, neutrons are neutral. And so when you fuse 2 heliums together, normally it'd be like a magnet. You've got protons with a positive charge in each helium nuclei, and they want to push apart because they have positive charge. But if you're strong enough, just like with a magnet, you can push them together, even though the magnet is trying to push those poles apart. Same thing happens with fusion. You keep doing that. But as you add more and more protons or more helium nuclei, the force gets stronger, and it gets harder and harder to overcome the repulsion. And eventually, when you get to helium, to iron, it's basically impossible. You cannot fuse anything more. You don't have the energy to actually do that. So that's as far up the periodic table that we can build chemical elements through fusion. So that's how a third of the periodic table comes, through those exploding big stars and fusing helium together. But that, again, that's only a third of the periodic table. So what do we do for the rest of it? Well, a lot of it comes from small stars like the sun. not right now, where it's happily just burning helium, hydrogen in its core, and will do so for another 5 billion years or so. But at the end of its lifetime, you extinguish the hydrogen and the helium in the core, and while it doesn't explode as a spectacular supernova, it does sort of puff off its outer atmosphere in a spectacular way as well, and you end up with planetary nebulae. And this is the Ant Nebula, and the nebula formerly referred to as the Eskimo Nebula, which is no longer called that. It's NGC 2392. And that's, a sneak peek of what the sun will look like in 5-6 billion years or so, when it finally sends off its outer atmosphere. And again, the color coding that you see there in these planetary nebulae are different chemical elements. Things like carbon and nitrogen and lead and tin and things like that all come from these sorts of stars. Now, the way they do it is not, I've just described how everything up to iron is more or less built by fusing helium together. But again, once you get to iron, force of repulsion is too strong. You cannot fuse these things together. But what you can do is you can make use of neutrons when you get to that point. Neutrons are, just like I said, neutral. And so if you are, for example, silver sitting right here, if you could not fuse any helium onto it because the force of repulsion is too strong. But if you've got free neutrons floating around and you add a neutron onto this silver, it moves over here on this chart of nuclides is what we call it, but it's unstable. It radioactively decays, and when it does that, it changes that neutron into a proton and it becomes cadmium. And that cadmium can capture another neutron, another neutron, another neutron, another neutron, another neutron. But this one is radioactively unstable, and so it decays and it becomes indium. If you collect another one, it's radioactively unstable, and it turns into tin. And this is how we move our way up through the periodic table to heavier and heavier and heavier chemical elements. It's through the capture of neutrons. And that really is all of stellar nuclear, a good fraction of stellar nucleosynthesis in sort of 3 minutes or so. Everything up to iron through fusing helium, more or less everything heavier through capturing neutrons. And that's where all of those things like tin and lead and scandium and all kinds of other weird and wonderful elements come from, through this neutron capture process. Okay, so I promised to go through a few more Guinness Book of Record categories. We have the ability now with various satellite missions and ground-based facilities to measure the temperatures of now probably billions of stars, maybe even more than that, by taking images in multiple bands and looking at the colors of the stars, or taking spectra and looking at the light and using model atmospheres to determine the temperatures. We can get a pretty good handle on, like I said, probably upwards of billions of stars now. And some stars are hot, some stars are cool, and it always begs the question, when you've got a whole bunch of things with a number attached to them, what's the biggest and what's the smallest? In this case, what's the hottest and what's the coldest? So this is the current record holder. The hottest thing that we've been able to measure. Now, I guess I should probably qualify that. It's the hottest kind of, let's say solid, but kind of solid entity, if you like. There are hotter gases, hotter plasmas. The plasma in the outer corona of the sun, or in some clusters of galaxies, is much, much hotter. You can be up to billions of degrees, tens of billions of degrees in some cases. But in terms of sort of an object that you could sort of point to and hold, if you like, this is the record holder. It's the Red Spider Nebula. It is marginally available, I think, in the northern hemisphere, but it'd be pretty far south. I can't remember. No, maybe, I think its deck is around 20 degrees or so. So I'm not sure when the best time to see it would be. It's pretty faint, probably about 13th magnitude, if I recall. And it's not so much the nebula around it. It kind of looks like a tarantula, which is why it's called the Red Spider Nebula. It's the object down in the center there. It's a white dwarf, a very hot remnant of a star like the sun, before it starts to cool and fade away. But when that star first forms, it's generally very hot. And this one is very, very hot. So it's about 300,000 degrees above absolute zero. So that's about 1,000 times hotter than anywhere on Earth, for some context. And it's about 60 times hotter than the sun. Now, there may be a star out there that might be a little bit hotter, but amongst the sort of billion or so that we have been able to determine the temperature, this is the current record holder as the hottest, I guess you would call it, object, if you like, in space. Conversely, at the other end, what's the coldest thing? It's another nebula. It's a protoplanetary nebula. So it's an object that's on the way to becoming a planetary nebula. It's in the beginning phases of it. Lurking down the center of that is also a white dwarf, but it's not the white dwarf here that is kind of the cold thing. It's the plumes of gas in the outer atmosphere of the star that is being blown off that is incredibly cold. It's about 1 degree above absolute zero, minus 272 Celsius, if you like your Celsius scale. The reason why it's really, really interesting, well, for a number of reasons. First off, it's just super cold, and it's the coldest thing that we know of. But this was again, up to a year ago, if you'd asked me, I would never guess in a million years there was anything naturally that was that cold. Now, you can go into a lab and supercool helium down to a fraction of a fraction of a degree above absolute zero, but that's kind of cheating. In nature, though, if you'd asked me a year ago, I would have said I think the coldest thing in space is the energy that's left over from the Big Bang today. It was obviously incredibly hot. You could go way back in time, but today those photons, which are all around us now, 1 in 10,000 photons around us. Is leftover photons from the cosmic microwave background from the Big Bang. So if you took a cubic centimeter of the space that you're sitting in right now, I think there's something like about 300 photons from the cosmic microwave background going through that right now. So they are all around us, and we can measure them, and we can measure it's a photon, so it's energy. So we can, just like you can measure the temperature of a flame through the photons that it gives off, you can measure the temperature of the cosmic microwave background, and it works out to about 2.7 degrees above absolute zero. And sort of naturally, I thought that was the coldest thing around us, and that was kind of what I had been taught when I was younger. So it was quite a surprise to me to see there was something actually colder than the cosmic microwave background. Now, if you have a speaker come and talk about cosmology and the content of the universe, how fast is it expanding? How fast is it accelerating? What's its ultimate fate? The primary way that we sort of approach those questions is looking at the cosmic microwave background. We look in different directions on the sky and we measure the temperature. One direction, it might be 2.7001 degrees. Another direction, it might be 2.6999 degrees. There's subtle little temperature differences from point to point to point across the sky. And the distribution of those subtle temperature differences encodes the entire history of the universe, the cosmology of the universe, and all the exciting discoveries that we've made over the last 20 years have been confirmed and built on through the study of the cosmic microwave background. But if you want to study the cosmic microwave background, again, it's very, very cold. And the problem is everything around us is so much hotter than that. I mean, you couldn't study the cosmic microwave background easily sitting here, in my kitchen where the temperature might be 20 degrees Celsius. So it's, way, hundreds of degrees warmer than the cosmic microwave background. It'd be very difficult to sift out the heat that's around me. And even if I could, I then have to worry about the heat of interplanetary dust. I have to worry about the heat of the interstellar medium and the dust that's in the interstellar medium. All of that contaminates the signal that I want to study with the cosmic microwave background. And an enormous amount of work over the many decades has gone into eliminating all that foreground warm stuff so we can actually just see the cosmic microwave background. But and so that's where the effort has been, eliminate anything that's too warm, basically. And what we've learned, and it's only very recently, is that, and something we hadn't really considered, is that there are things that are colder than the cosmic microwave background, and this is one of them. Now, there's not many of them, might only be 1 or 2 that have been discovered where on one point in the sky, there's actually something colder than the cosmic microwave background. And so you actually, if you're getting into the fine details of cosmology and you want to just see the cosmic microwave background, not only do you have to remove the foreground warm stuff, you actually have to remove the foreground stuff that's too cold. Again, something that up until a few years ago, we hadn't really given any thought to. We didn't expect to find anything that cold. But this gas cloud floating around this white dwarf is colder than the cosmic microwave background, and it is one of the special little things that you have to correct for when you're doing cosmology study. So that is the current record holder. Probably you'd be hard pressed to find anything colder than that. You're all getting very close to absolute zero. There is nothing below that. And so if there is, it's going to be remarkable, but this is far and away the coldest place in the universe that we have discovered. We talked about those massive stars that form are responsible for more or less everything up to iron in the periodic table. Now, when they explode, you get these spectacular supernova remnants. You can see all the chemical elements in the colors that I showed you in the picture. What's left over behind might only be a fraction of the original mass of the star. Might be 5%, 10% of the mass of the star that exploded is left over. But what's left over, it's one of two things. It's either a black hole, sort of a stellar mass black hole, not the sort of supermassive ones that I talked about before, or it's a neutron star. And a neutron star is basically what it sounds like. It's more or less just a gigantic ball of neutrons to first order. And these balls of neutrons, when they merge together, and things like a lot of those chemical elements that I showed you, many of the heavy ones, the heavy chemical elements, they require neutrons. Things heavier than iron require neutrons. Some of that comes about from stars like the sun at the end of their lifetime. There's actually lots of neutrons floating around, and that's where we get our tin and our silver and our gold and various other heavy elements. But these neutron stars are also fantastic sources because there's that enormous number of neutrons. Now, if you just have a whole bunch of neutron stars sitting by itself, okay, it doesn't really do much. But if you can merge two neutron stars together, then the energy involved and the release of all of these neutrons mean that you can synthesize heavy elements as well. But that's a whole other different point. The reason why it's in there is that when you have a big star, all stars are rotating a little bit. Our sun is, stars that are much heavier than the sun also rotate. They may spin at slow rates, some spin a little bit quicker, some a bit slower. But what happens when you blow off the atmosphere during the explosion, you're left with a remnant, but it's a tiny, tiny, tiny fraction of this big star. And so it's a process called conservation of angular momentum. It's just like the figure skater analogy. When the figure skater is spinning around with their arms extended, they're going at a certain rate. If they pull their arms in, angular momentum is conserved, and so they spin faster and faster. This is effectively what happens. You've got a spinning star, and you very rapidly blow off the outer atmosphere, and you're left with something much smaller. So it's just like this figure skater pulling their arms in, except you pull it in really small. And what happens is that slowly spinning star rapidly spins up to conserve angular momentum. And now we've got tens of thousands of rotating neutron stars, which are called pulsars. They were discovered by Jocelyn Bell Burnell, pictured down there, is a good friend and a honorary graduate of the University of Hull. And she works with us closely on a number of things related to increasing the participation of women in the STEM subjects. A number of our students and interns with Jocelyn. She is the one who discovered the pulsars and was overlooked for the Nobel Prize, but again, that's a whole other different story. Now, as you study tens of thousands of pulsars, some of them rotate a bit slow, some of them are a bit fast. They're all rotating. And again, we love to make lists. And so we make the list of what is the fastest spinning object. And it's a pulsar that is left over in this globular cluster called Terzan 5. The remnant weighs twice that of the sun, but it's only about 20 miles in diameter. So you've really taken a big thing, squished it down really small, and it's spinning incredibly fast. So about 716 times per second. So it's about a quarter of the speed of light. Now, it's very difficult to make the analogy. If you stand on the surface of the Earth at the equator, watch it going around, you're moving at sort of about 1,000 miles per hour. If you wanted to go at a quarter of the speed of light, you'd have to stand at the equator and spin the Earth up, not for a 24-hour spin, but to about a half second or so, I think it was. The problem is you couldn't do that because you'd spin so fast that centrifugal forces would blow apart the Earth if you tried to spin it that fast. I think before you got even remotely close to the ability to do that. The thing about pulsars and these neutron stars is the gravity is so strong. You've taken something really heavy, made it really, really small, And so you can spin these things super fast before they actually break up. And in fact, the theoretical best guess is right around this value. It is really about a quarter of the speed of light before centrifugal forces will win out over gravity, and you spin this thing so fast that it will break up. So again, it's unlikely. This is an incredible, remarkable success for the theory of pulsars and the strength of the gravitational field, their size, their mass. The prediction was that you would have a value around that. That was how fast you could spin them. You should never, ever find a pulsar spinning faster than that, because it would break apart and you would never be able to detect it. And so this is an incredible confirmation of a very challenging theoretical calculation. So it's very unlikely that we will find anything that spins faster than this anywhere in the universe. Otherwise, it would violate this now well-known theory. And very quickly, the last couple, what is the loudest thing in space? Now, we don't normally, again, much like we don't think of smell in space, we don't necessarily think of sound in space, because, again, to first order, we think of space as a vacuum. The reason you can hear my voice is, if we're sitting in the same room, we have an atmosphere, and so my voice is a set of pressure waves. It's kind of like a caterpillar working its way across towards your ear, or here in this case towards my speaker, where the atmosphere compresses and then uncompresses and compresses and uncompresses. It requires a carrier for the sound wave, and that is the atmosphere. So if you're in a perfect vacuum, there's of course no sound, because there's nothing to carry any pressure waves. But again, much like as you move through space, you can find places that are not a vacuum, and so you can smell things if you like. Because there are places that are not a vacuum, that means sound can propagate there. You just need anything. It doesn't have to be the air or the water around us. As long as you've got a medium to carry the pressure waves, then you can create sound. Our sun is like the Earth. It creates, it has sunquakes like earthquakes, and those sound waves bounce around inside of the sun. Now, if the sun was nothing could escape the sun, and there was no atmosphere above the sun. Now, the reddy bit glowing around there is the corona, the outer atmosphere of the sun. If that didn't exist, it was like a hard shell. Sound would bounce around inside, but it would never escape because there's nothing to carry the sound. But because there is an atmosphere, it does mean that the sound can propagate. And if you could fly to this corona, this outer atmosphere, and listen, you would actually hear some. You would hear those sound waves bouncing around and leaking into the atmosphere. And if I was doing this experiment in a school, what I would do is I would get them to point out, who's the loudest kid in the class, and I would get that kid to stand up, and I would get them to scream at the top of their lungs and tell me, okay, that's about 100, 120 decibels in terms of the decibel scale that we use for volume. And it's a very confusing scale, but it's basically what we call logarithmic. Something that's twice as loud is not twice as large in terms of the decibels. But at the sound here, it's about 300 decibels. And for context, that would be the equivalent of taking not one kid screaming, but the equivalent of taking several trillion kids. So 1,000 billion screaming children is more or less what the sound of the sun would be. Now, if you could listen with your ears, you wouldn't actually hear anything because it's very subsonic. So much like when I was speaking, I go lower and lower and lower and lower, and you can go lower and lower, and eventually you can't hear it, but you can sort of feel that sound. You go incredibly subsonic, about 40 octaves below sort of middle C on the piano. But if you had the right sort of ears, this would be the loudest thing. Now, there almost certainly is louder places in space, but it's an incredibly difficult measurement to make. Probably the gas that exists between the galaxies and clusters of galaxies would probably be even louder, but even more subsonic, if you like, because the atmosphere is even more dilute. But in terms of what we can measure, at about 300 decibels, this is the loudest thing that we can measure, and it happens to be right next door to us. A different way of thinking of chemical elements is, as we all know, there's some elements that are rare, there's some that are very common. Hydrogen and helium, very common. Vast majority of the cosmos is made up of hydrogen and helium formed in the Big Bang. And then most of the rest of the chemical elements through the processes that I just described in terms inside of stars. Now, this is a different way of plotting the periodic table. It's sort of just shows you how common or rare a particular chemical element is. Things like hydrogen and helium, very common. As I move to heavier and heavier elements, the thing which is the rarest, not counting things that are radioactively unstable, like uranium, the rarest stable element is this one, tantalum. How rare is it? Well, if you took a swimming pool and filled it with sand, kind of an analogy I used at the beginning, you'd have about a trillion grains of sand. And if you color coded one of those as red, if you like, that would be tantalum. So you got basically one atom of tantalum for every trillion atoms of hydrogen. So 10 times rarer than gold. So the rarest stable element in the universe. It's incredibly valuable. It's formed through this neutron capture process that I talked about in stars like the sun at the end of their lifetimes. It is very rare. It's rare on Earth as well. It's incredibly valuable. It's what we call a conflict resource. Great War in Africa was fought. The biggest war outside in the 20th century after World War II was the Great African War. It was fought over tantalum mines, just because of the sheer value of tantalum. It's a unique sort of chemical element. It's what we call resistant to any biological processes. So it's often used as a coating on implants, knee implants, hip implants, because again, it's immune to biological processes. It's also it doesn't corrode at all. So it's very valuable in terms of your smartphones, your tablets, your laptops. They've got various capacitors in there for storing charge. They're largely made out of tantalum. One of the reasons that people want to recycle, mobile phones, for example. There's lots of good reasons for doing it, but also part of it is trying to recover the tantalum that goes into the things like capacitors, because it's a limited resource. The current rate that we're mining it, the vast majority of it is in Africa. There's about 50 years left of tantalum on Earth, and given the way we move further and further into an electronic world, we're going to have to find an alternative to tantalum, because we can't power all of the capacitors and create all the capacitors we need using tantalum. It's also a really interesting element if you want to create, if you want to take nuclear weapons, which are already scary, and you want to make them really scary, what you do is you coat them in a layer of tantalum. You can do it with cobalt. You've probably heard the term cobalt bombs, tantalum bombs. What happens when the nuclear weapon explodes is an enormous amount of energy. And if you have a coating of tantalum, for example, what you can do is create, you can free up neutrons as the energy interacts with the layer of tantalum. And you can, just like the neutron capture process that I showed you, you capture neutrons and you can create something which is radioactive that then decays. Radioactive tantalum is nasty stuff. It has a half-life of about 3 months, and it creates an enormous amount of energy. So you can take powerful nuclear weapons and make them hundreds, thousands, 10,000s of times more powerful. They're, again, something I hadn't really heard about until a few years ago. They form the basis of things like, if you watch films like Dr. Strangelove and Beneath the Planet of the Apes or On the Beach, all of them are based around these salted nuclear weapons, and those salted nuclear weapons are based around basically putting a coating of tantalum around a nuclear weapon. So this is the rarest thing in terms of the rarest stable element in the universe, and a really interesting and useful one, also a really scary one. And the last thing I'll end on is what is the scariest thing in space. And it's not this is our Milky Way galaxy. As I play God for a second and step out of the galaxy and look down on it, we've got about 100 billion stars. They're all going around at about 500,000 miles per hour in nice circular orbits, more or less within the plane of the galaxy. We sit sort of halfway out in the suburbs in a very quiet part of the galaxy between two big spiral arms. It's a very underdense region where there's not a whole lot going on. We move at more or less the same speed as the spiral arms. These are all probably important little bits of the piece of the puzzles of the development of complex biological life, because we don't run through the spiral arms or don't get hit by the spiral arms regularly, because we're at this thing called co-rotation. We move at the same speed as the spiral arms. So that gives us sort of long-term stability, if you like. Now, here's one little star. it's a little bit fainter. I think it's maybe about 12th magnitude or so. It looks to the eye like more or less any other star. It's also a K-dwarf, maybe half the mass of the sun. But unlike the majority of the stars that are happily moving at 500,000 miles per hour in nice circular orbits, and we're moving more or less in lockstep with them as we go around the galaxy, this one's a bit of a rogue, and it is moving basically straight towards us like the barrel of the gun pointed at us, 60 light years away right now. It's moving at 30,000 miles per hour. We've got exquisite observations with the Gaia mission up in space now, which tracks the if you like the proper motions, if you like, on the sky of this thing. And it is coming. We know its orbit really well, and it's moving right towards us at that speed. And to put it into context, this is, again, a really interesting plot which shows going forward in time, going back in time to the left. And because we can measure with exquisite precision how these stars are moving around us, we can work out going forward in time and back in time. If I go forward in time, I can work out how close a star that's near us now might get to us, its closest approach, or I can look back in time and figure out the stars that are around us now, what was the closest they were ever to us in the past. And for context, this is roughly the distance to, say, Proxima Centauri. You're looking at about 3 light years at this point. And so there's not much in the recent past, 10 million years, or in the future that comes anywhere closer than sort of, a few million light years from us. But you can see this one green dot right there. In 1 million years from now, this star, Gliese 710, is going to get incredibly close to us. In fact, it's so close that it's actually going to pass through our solar system. Outside of the sun, it'll be the brightest thing in the sky. It's not going to get down as close to where the planets are, but it's going to move through the outer part of the solar system through what we call the Oort cloud, that reservoir of billions, possibly trillions of comets. And so it's going to move through slowly this big, heavy thing, which will affect, because of its gravity, it is going to shake loose and disturb this cloud of comets, which are loosely held on by gravity. But because we don't hit the spiral arms very regularly and there's not much around us, they're held on by gravity, those billions and trillions of comets, for the most part. Every once in a while, one gets dislodged. And 65 million years ago, one of these comets probably took out the dinosaurs and the other, 80% of the species that existed at the time. But this is what's going to happen in 1 million years from now when this actually goes through us. If there's anything that's going to, we'll probably wipe ourselves out before that point in time. But in 1 million years, which is fairly short in terms of, geological and astrophysical timescales, this thing is going to go through the solar system. The best guess, and it's very difficult, these calculations, but the best guess is it will shake loose tens of millions of comets over the subsequent 1 million years that will rain down into the inner part of the solar system. Okay. Solar system is mostly empty. Most of those tens of millions of comets are going to miss us, but all it takes is one. And every once in a while, one does. So if you're someone who likes to observe comets, it'll probably be a fantastic time, because the best guess, again, is but once a month, a new naked eye comet will appear in the sky. So you're going to have a rich reservoir of comets to study. If you like to study stars and galaxies, the sky actually might get a little bit crowded with comets, and so it may be a bit disappointing in that sense. But we all just have to watch out for that one. Now, again, Elon Musk may not be around in 1 million years, but maybe he can resurrect Bruce Willis and use some sort of Armageddon style thing to get up there and deflect all of these comets before they ever get a chance to hit us. But if something astrophysical is going to take us out, probably it's not going to be an asteroid or something like that. It could very well be in 1 million years' time, one of these comets that gets shaken loose by this star passing through our solar system. So it will be an exciting time, whether it's good or bad. You'll have to stick around and see. And so just to wrap up, you've got a recording, so if you do want to follow up on any of these sorts of things, you can do so. I won't go through and read them all. But hopefully you picked up a few things that you haven't seen before. And if you have any suggestions to feedback, please do. And if you have any questions, happy to entertain them. And thank you very much for giving up an hour of your time to chat with me.
Thank you, Brad. As always, you've given us plenty to think about. And I'm going to have to change my talks to primary school children when I'm talking to them about the end of the world in about 5 billion years time when the Earth.
I do. When I do my How the Universe Will End,
About
I have a talk which steps through that and all the things that you encounter along the way. Assuming we get past that million-year one, then I do go through it.
Yeah, I've had difficulty getting the kids off the ceiling with 5 billion years. I'm not too sure how I'm going to manage with 1 million years. I think I'll just leave it out of the talk and keep the kids calm. While people are framing their questions and the like, can we go back to the Boomerang Galaxy? Oh, the Boomerang...
That Boomerang Nebula, yep.
Nebula. And the coldest place. Is the nebula expanding or contracting?
It is expanding. The speed at which it's expanding, and that's partly why it's so cold, is that it's expanding incredibly fast. Somewhere I've written down the number. Where is it? So it's about 400,000 miles per hour. So it's about 1/1000th the speed of light that it's expanding at, that outflowing gas.
Okay, so presumably that goes some way to explaining why it is as cold as it is.
Yeah, that's it exactly. And it's kind of a cheat because the previous slide I talked about what is the hottest thing, and I avoided plasmas and gases and things like that. And I pointed to an object and said that white dwarf, this solid object, if you like, is the hottest thing. And then the very next slide I cheated a little bit because it's not a solid thing, if you like. It's the surrounding gas that's outflowing incredibly fast and brings its temperature down to that level. But regardless, it does have an imprint on the, if you like, the cosmic microwave background. So it caught my attention, and it was something I didn't know about until a couple of years ago.
Okay, so have we got any questions for Brad? As always, if you can put a digital hand up, that'll be lovely. Otherwise, wave at me and I will try and spot you. Lewis, can you unmute yourself, please, Lewis?
Hi.
Hi, can you ask a question, please?
Yeah. For the richest place ever,
Yep.
How would scientists and astronomers know if there is a diamond in the center of a planet?
Yeah, what it comes down to is that we know this is it's a rocky planet, given its size and how heavy it is. So we know it's a rocky planet, and then you make the guess at that point in time. What is this rock likely to be made of? And because carbon is so common, a large fraction of it will be carbon. It won't be 100% carbon, but we know with our models, therefore, that if we assume there's a reasonable amount of carbon in this planet, and given its size and its mass, we can make our best guess as to what the pressure is inside. And because we know how much pressure you need before you can, if you like, crush carbon into diamond, we can make a best guess that a substantial fraction of that, you don't have to go too deep into this planet before the best guess as to what the pressure is high enough to turn that carbon. So there's a few ifs along the way, which makes it very difficult to give you a precise measure as to exactly how much is in there. But carbon is very common. It's likely to be a big part of any sort of rocky planet. And if the pressure is high enough, you can crush it. You have to go, you could take you could take charcoal here on a chunk of coal, take it, to the bottom of your pool, and the pressure gets higher. You can feel that pressure in your ears as you go deeper and deeper. That's not enough. You go to the bottom of the ocean, that's still not enough. The pressure is enough to crush you and blow out your ears, but it's not enough to turn that coal into diamond because it's just not high enough. You have to go deeper and deeper and deeper, but the pressure gets higher and higher and higher, and eventually the pressure gets high enough that you can convert that carbon into diamond. So while we can't go there, grab it, and dig into the bottom of that Cancri 55E to see the diamond itself, the size, the mass, the pressure involved, and the likelihood that there's carbon associated with this rocky planet tells you the pressures involved means it's not going to be standard carbon. It'll be crushed into diamond.
Okay, Lewis.
Okay, thank you.
Okay, and Roy Gunson,
Yeah, just a query on the rarest material, tantalum. On your chart of the periodic table, I did notice that element 61, promethium, didn't have a mechanism for creation.
Oh yeah, there's some. Yeah, there's some which are. Yeah, so is it technetium maybe, which is I think that I'm just looking at the element number to make sure. There's a couple of them that are for example, radioactive, or they're not stable.
Right.
So, for example, technetium is. That's not. I'm just looking at my plot. It's not. So, technetium is one which there's no state. Much like it doesn't have a stable isotope. We see it in nature, but it doesn't stick around. So that is one where we can create it in the lab. It's created in stars like the sun, but it does not have a stable isotope. And I think the one like promethium, which number did you say it was? It was like 61, something like that. Yeah, so it gets created not so much in through sort of the fusion or the neutron capture process. You can create it in nuclear reactors, for example, sort of artificially. You can create it, and does get created in nature through its fission process. So you can create uranium inside of a star, and then some of that star through nuclear fission, not fusion, but fission, will form. So it's kind of a daughter element, or a daughter isotope would be the terminology, I guess, rather than one that's synthesized inside of the star. It gets synthesized from the fission of uranium. Now, what stars are responding? Not 100%, but I'm going to assume it's like high mass stars or merging black holes or merging neutron stars, but that's a wild guess. Somewhere where you can get somewhere where you've got a source of uranium that can undergo nuclear fission will create it. But again, I guess the simplest answer is that it's a daughter isotope, a daughter element, rather than a primary.
Primary element.
Well, that's a reach for me.
Okay, so anybody else got any other questions? I'm looking around. Mike, can you unmute yourself, please?
Hi, Brad. When you were talking about rotational speeds of pulsars, can we intercept the beam from both poles? And if we can, how do you determine if you're intercepting the beam from one pole or two in order to determine the rotational speed?
Yes, that's a good question. I'm sure someone on pulsars would give you an immediate answer to that because it's probably trivial to them. Yeah, I'm just looking at the simulation of the spinning thing.
Have a wobble on it, so
I think I guess you would have to have exactly the right viewing angle. Yeah, I'm trying to think, if you have perfect symmetry, and I mean, I suspect what the case would be is you would see both of them, because even the way the animation was showing, it makes it look like only one would ever hit you, just because of the exaggerated way that it's, if you were really close to it, for example, yes, maybe you would be aligned in a way that only part of it swept over you. But I guess if it's perfectly symmetrical and it's really, 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 really far away from you, as it spins around, if the North Pole happens to sweep over you, or its cone sweeps over you, then the South one is probably going to as well, simply because it's so far away, and the field of view of the telescope is going to be large enough to encompass the northern part, which might sweep across the northern part of the telescope, and the southern part that might sweep across the southern part of the telescope. But if you were really close, depending on the viewing angle, then maybe you would only see one of the beams that crossed over your field of view. it's sort of a geometrical problem that I'm having problems picturing in 3D.
Okay, Mike, have you got a follow-up?
No, thank you. That was it.
Okay, and I'm still looking around, and I'm still looking for questions, and I think we're going to call this once, we're going to call it twice, and I think we're done for... Oh, no, that Roy Gunson's just come in with another question. Go on then, Roy.
Yeah, going back to the diamond planet. I mean, if the pressure is high, wouldn't the diamond liquefy? Wouldn't it become molten?
Yeah, I have no idea. That's, you know, that's,
Sorry,
try try Googling, can you liquefy a diamond?
You're gonna really annoy a lot of women here. You do
10 million times the atmosphere's pressure. Apparently, it melted, then re-solidified. I had never even thought of that, Roy, in my life before, and now I'm going to go. I can see myself going down a rabbit hole of Google now on the temperatures and pressures to liquefy diamond. I never even thought of that one before.
it'll turn into a diamond about 1,000 miles of diameter.
Oh, that's really interesting. Yeah, yeah. You can. There is a whole lot of stuff on this. Yeah, you can melt them down. It changes its structure so that it is no longer a diamond, because you obviously break down the fundamental way in which the carbon configures itself into a diamond, and so I don't think you can melt it down and then I don't know. I don't know how you re-solidify it and it forms a diamond again. I don't know. I need to look at this because now you piqued my curiosity.
Just a word of warning, Roy, don't go around experimenting with Eleanor's jewellery.
No.
Okay, Peter Lloyd, can you unmute yourself?
It was just a thought while we're on the question of diamonds, and you were talking about diamond rain on Uranus and Neptune, and I thought that maybe in 4,000 million years it might have sort of run out of a source of carbon, unless there's some way of taking the carbon back out of the diamond.
Yeah, I think you are probably right. I don't know how it gets cycled around. I don't know how the atmosphere might evolve with time. We don't have direct evidence that these micro diamonds exist, but they've simulated in the labs, the conditions. We have a pretty good idea what the density and the pressure environment is, what the atmosphere is actually made of in these planets. And so people have done this experiment in the lab and were able to create these sort of micro diamonds. So it is kind of an indirect proof that they are there rather than a direct observation. But yeah, how, whether it's stable, if stable and nothing changes, then what's there is there, and it wouldn't disappear. I would guess if you somehow could, you'd have to disturb the equilibrium that probably exists right there now, and maybe, I don't know whether scooping out those little micro diamonds is enough to disturb the equilibrium that you would allow you to create more micro diamonds. I don't know. That's
Yeah, I think it was Arthur C. Clarke, wasn't it, who suggested the center of Jupiter was one enormous diamond.
Yeah, I mean, if you wanted to, I guess if you could get, wrap a big blanket around the entire planet and crush it down, you could turn it all into diamond as well. But it's probably not the most efficient way to make your money.
Okay, ladies and gents, and I think we're going to call that tonight. Brad, once again, many thanks for stepping in so late and bringing a whole new meaning to the term kitchen astronomy. And, just to, once again, ladies and gents, can we give Dr. Brad Gibson a big Mets Swinton Astronomical Society? Thank you.
Thank you, folks.